Hello there guys, Teacher Krishna here and welcome to our following class for the 4th unit. So just like you know, this is a class that is part of Beehive School and 10th High School. We are working on the subject physics and week number 28. Let's start with our ending mind for today. Students will be able to use Canva to synthesize the content from topic 3.05. Here you have a summary of the activities for today. Read topic 3.05, complete practice 2 and 3 from page number 2, access the platform Canva and synthesize the content of the lesson in a mind map, and take the assessment for topic 3.05. So, in order to access to Canva, you need to go to canva.com and select one mind map that actually calls your attention and you think you can use adequately to synthesize the content. And you can use it as the summary for today. So the mind map is basically the summary. You don't have to do anything else besides that. And of course, the activities that are specified here as the assessment from topic 3.05. Here you have the rubric that I will use to evaluate your mind map in Canva. So you can go ahead and stop the video if you would like to check a little bit more what I'm going to be evaluating. Okay, let's start with force diagrams and friction. So a free body diagram. It shows all the forces that are acting over a specific object. It makes it possible for physicists to predict the behavior of such objects. The object is usually represented by a point, while the forces are shown as vectors that are proportional to the size or length of the acting forces. Each force must be labeled. In some cases, some axes can be included to visualize the direction of the forces in a better way. For illustration purposes, the object itself can be drawn. So here you have the representation of a very simple free body diagram. We have a book that is at the top of a table, and we are going to identify and label the forces. We have one vector that goes down, which is the gravity, and one vector that goes up, which is the force that the table applies over the book. And this previous example was very simple, but there are some other diagrams, just like this one, that are a little bit more complex, that identify, for example, the force that is being applied downhill, the force that is being applied frontwards. We also have the normal force and the weight. All right, so now review the steps for making diagrams from page number 1. So go to page number 1 in Agilex and review the steps that you have right there in order to know how to create the diagrams that we had before. And here you are going to find some examples about what we were talking about before. All right, so we have this diagram, and basically it is an object that is suspended by a rope that is attached to the object. So what forces are we going to find right here? We're going to find the tension, which is basically the force that is in the rope that is attached to the object. And of course, we have weight. So the tension is going to be signalized as a force that is going upwards, and the weight as a force that is going downwards. All right, let's continue with the next example. We have this one right here, which is one of our previous examples, which is basically a book that is on a rest position at the top of a table. So notice something very important. When an object is in a rest position at the top of another object, which is in this case a table, remember that the object, that is the base, is going to exert an equal and opposite force to the object, which is basically going to be the normal force. That is why it's being represented as upwards. And we also have the weight, which is the gravitational pull that the object is suffering from Earth, which is represented as a vector that goes downwards. And lastly, we have this one right here, which is a little bit more complex. So basically, we are analyzing frictional force. And notice that a frictional force is any force that is going to obstruct the motion of the object. And of course, it is going to be in a different direction or in an opposite equal direction to the force that is being applied. For example, if I'm pushing a box to the front, the friction is going to come to the back. And it is going to be a force that at some point is going to stop the box from moving. So we have a force that is being acted to the front, the friction that goes to the back. We have our normal force, which is just like we analyzed before. And lastly, we have our gravitational pull, or we can also say that it's our weight. We also need to analyze another term that is very important, which is the coefficient of friction. So, in order to do that, we have this table right here that takes into consideration the kinetic frictional force and the normal force. And right over here, we have our formula for finding the frictional force, but it also includes the coefficient of friction. So just notice that capital F and lowercase f stands for frictional force. Then Fn stands for normal force. And this symbol that you have right here that reminds us of a letter M is the coefficient of friction. So taking into consideration the kinetic frictional force and the normal force, we can actually implement the difference in each one of both of them from the start and from the end of the study that we were doing just before. So they both start at 0 because the object we are analyzing is motionless. So we are going to analyze the difference in between both of them. So regarding the kinetic frictional force, it starts in 0 and it finishes in 1.5 newtons. And the normal force starts in 0 and ends up in 7.5 newtons. We divide it and we are going to notice that the frictional or the coefficient of friction is 0.2. Okay. Now we're going to go with some important concepts that are related to this coin on the water. And the coefficient of friction changes from an object in rest to an object in motion. So we need to analyze that there are two types of friction. We have the static friction, which is the friction that is applied to an object in rest. Okay? So if an object is not moving, we are talking about static friction. And we also have kinetic friction. It is the friction that is applied to an object that moves at a constant speed. This is usually lower than the static friction. So, one more time. Static friction is for motionless objects, and kinetic friction is for objects that are moving at a constant speed. All right, and now we're going back to the example that we have on the right. Imagine an object that is falling inside a body of water. The more it accelerates, the more resistance to its motion increases as well. At some point, both forces will become identical, which will cause the object to keep on falling, but not accelerate. We know this as terminal velocity. Let me rephrase all of these mixed up words for you. So, imagine a coin that you dropped in the ocean. So the gravitational pull is going to start attracting the coin to the center of our Earth. So let's say that at some point the coin is going to manage to get its maximum speed. This is not accurate, but let's say 2 kilometers per hour. So remember that we are considering the friction, the frictional force, and also it stops the speed from increasing. So at some point, this maximum speed of 2 kilometers is going to be the maximum speed that the coin can achieve. Of course, it will continue falling, but at a constant speed. And basically, that's what we know as terminal velocity. We are going to talk about frictional forces as well. So they're always present when two surfaces are in contact, no matter if they are solid, liquid, or gas. Solid as in the book and table, liquid as in the ocean and the coin, and we can also analyze in some gases. And friction is always present. And any force that stops motion is known as friction. We have kinetic friction, the necessary force that a solid needs to keep on moving at a constant speed over another surface. And we also have static friction, the necessary force that an object needs to start moving, which are pretty much terms that we have analyzed before. And here you have a diagram that represents several forces that are acting upon an object. We also have our weight, we have our normal force, we have our the force that is pushing the object right straight ahead, and the frictional forces that are going to be opposite to the forces that push the object in a certain direction. All right, we also have the laws of friction. And friction is independent of the areas of contact. So the objects themselves already have a coefficient of friction. So not necessarily because they interact with one or another substance that is going to change. So the atoms or the objects we analyze always have a constant kinetic or a constant frictional coefficient. The friction is proportional to the forces that keep an object in equilibrium. So, like I mentioned before, there are certain objects that are motionless, let's say. So, when you try to move them, they are going to remain still. Why does that happen? It's because friction is the opposite force that is actually obstructing the motion of that object. Just like in the experiment that you conducted last week. So basically you had several objects at the top of a surface, and you started inclining that specific base. But if the inclination was too little, the object will not move. Why? Because of friction. Until you actually increase the inclination or the angle of incident, and that will basically cause the object to start falling or to start moving. We also have friction occurs in fluids, which leads to a phenomenon of viscosity. All right, and lastly, we are going to analyze an example with everything we have gathered. So a 100 Newton sled with steel runners is on a horizontal steel track. The coefficient of static friction between steel on steel is 0.45. What is the minimum horizontal force required to start the sled to slide along the horizontal track? And we have part 2, which is the coefficient of kinetic friction between steel and steel is 0.25. What is the magnitude of the force needed to keep it moving at a steady speed? In part 1, we're analyzing static friction. And in the second section, we're analyzing kinetic friction. So let's go with part number 1. So basically, this is the weight of the object, but the object, or most likely the object's weight, is going to be equal to the normal force. So the normal force will be 100. We also have our coefficient of friction, which is 0.45. So we are looking for the force that is required to put the object in motion. We have our formula right here, so we are going to substitute our coefficient of friction, and we are going to substitute our normal force. We multiply it, and we find that the necessary force to put the sled in motion from a rest position equals 45 newtons. Let's go with part number 2. We have, one more time, our normal force is basically the weight of the object, 100 newtons. The coefficient of friction, of kinetic friction, is 0.25. So what is the necessary force to maintain the object's motion at a constant speed? And one more time, we are going to substitute our values. We substitute the coefficient of friction, we substitute our normal force, and once we multiply it, we find that the necessary force equals 25 newtons. And just so you can notice, there is one principle that we studied before. Static friction is usually higher than kinetic friction. And of course, since one is higher than another, the required force to put an object in motion is 45 newtons, is going to be higher than the one that requires the object to maintain its speed, which in this case is going to be 25 newtons. So that'll be about it for me today, guys. Thank you a lot for coming, and I will see you in a couple of minutes during the live session. It's been great seeing you all around. Goodbye and take care.